So this being a workshop on the Farrell-Jones conjecture and this being the last day, I figured that I probably don't have to say that much about what the Farrell-Jones conjecture actually means. And instead of saying, well, let's just do it for yet another functor, maybe it's a good idea to spend a little time on motivating why we should be interested in the Farrell-Jones conjecture for yet another functor. So let me start with the motivation for a theory and giving you an idea about why you as geometric topologists should be interested in this functor. And let me also say at the very start that it's a slightly complicated story, so I won't be providing full details. I will at least try to gloss over a certain number of technicalities and details, and we'll just have to find out what you let me get away with. So let's assume that we have a closed aspherical and also smoothable manifold of dimension n, and n will at some point be assumed to be sufficiently large. And a question that arises sort of naturally is, if we have such a manifold, can we understand its group of automorphisms? By which I mean self-homeomorphisms of the manifold. So we're actually interested in M as a topological manifold. And of course, there are different ways to interpret this question. I want to interpret it in the way that I'd like to compute the homotopy groups of this automorphism group. So what can we do? Now, if we want to compute only the homotopy groups, then of course it's enough to replace this guy by something weakly homotopy equivalent. So instead of considering the topological group of self-homeomorphisms that you will write down naturally, I like to redefine top M to mean the realization of the singular set of the group of self-homeomorphisms of M. Which is clearly the same thing if we only consider these guys up to, or if we only are interested in the computation of homotopy groups. Now, if we look at this space, then, or this simplicial set, then we can fairly explicitly describe what a simplex looks like. So if we look at a simplex in this singular set, then this is a family of self-homeomorphisms of M parameterized by, say, the P simplex, or alternatively we could think about this as a self-homeomorphism of M times delta P, which in addition is compatible with a projection down onto the simplex. That's really saying the same as we have a family of self-homeomorphisms varying continuously with that simplex. Now, if we think about simplices this way, we see that we have rather strict conditions, and that we can relax these conditions and still get the simplicial object, because if we want to define a simplicial set, then it's clearly enough not to have this diagram commute, but only that we have such a self-homeomorphism which restricts appropriately to the faces of a simplex. And if you do that, you get another space, which is called, or usually denoted, by top twiddle of M, and it's called the block automorphism space of M, and which is defined precisely as I just said. So you look at self-homeomorphisms of M times delta P, which are compatible with the face inclusions of the simplex. Since this is a weaker condition, you see that there is a map comparing these two. And now if we want to compute homotopy groups, and if we want to compare these two, we always know that there's a way how we can get a long exact sequence by taking the homotopy fiber. In this case, the situation is slightly better, because one can show that, or one knows that both of these guys can be de-looped, so both have a classifying space. And then we can extend this to a homotopy fiber sequence to the right by simply taking now the homotopy fiber of the map induced on the classifying spaces. And this is traditionally denoted by top twiddle M mod top M, even though it is not a quotient of groups. And now, of course, we have a map like this, and as I already said, this is a homotopy fiber sequence. So, in consequence, we get a long exact sequence of homotopy groups, comparing the homotopy groups of these three gadgets, top M, top twiddle M, and top twiddle mod top M. And, well, the question is, does that help us in any way? Now, the nice thing that we can say is, let me add this here in a separate box. So, this top twiddle mod M, in general, this is a very vague slogan. You can say this is approachable by the methods of surgery theory, whatever that is supposed to mean. Something explicit that we can say is the following. If you know that the fundamental group of M in fact satisfies the K and L theoretic Farrell-Jones conjecture, then you can conclude quite a lot about the homotopy groups of this block automorphism space, because they are trivial in almost all degrees. You know that pi I of top twiddle mod M is 0 for I bigger than or equal to 2. You know that the fundamental group of this guy is isomorphic to the center of the fundamental group. And you can also compute that its set of path components, or its group of path components, is isomorphic to the outer automorphism group of the fundamental group of your manifold. So, ignoring degrees 0 and 1, this in effect tells us that the homotopy groups of the automorphism group of M are up to shift the same as the homotopy groups of this homotopy fiber top twiddle mod top. And hence, we may focus on trying to understand this guy and computing the homotopy groups of this space. Now, of course, it's not clear that we have really gained much from this because, well, we've written down a homotopy fiber. The question is whether we can actually understand anything about that. But fortunately, there is a theorem due to Michael Weiss and Bruce Williams, which tells us something about this space top twiddle mod top. Namely, well, first of all, it says there exists a map. That's not too hard. What kind of map does there exist? There exists a map from top twiddle mod top to something else which has a more geometric description and which is unfortunately slightly convoluted to write down, so let me do that in several steps. So first of all, what you may do is we have fixed our manifold M. We can look at its space of H cobordisms. Which you should think about as built out of a simplicial set where P simplex is a family of H cobordisms parameterized by the P simplex. And there's a couple of details that you have to really nail down or to make sense out of that, but that's the idea how you build this guy. It's actually a simplicial set. You can take the realization. And then actually you don't consider the space of H cobordisms, but a spectrum of H cobordisms, so you have to deloop this guy. Plus, there's actually an additional construction involved which stabilizes the dimension of your manifold that I'm going to ignore. So let's think about this as the space of H cobordisms. And then let's also consider it as a part of the theorem that this guy carries a Z mod 2 action, which I don't want to explain. And if we know that this guy has Z mod 2 action, then we can take its homotopy orbit space. And, oh, I'm running out of space. Now, if we agree that H of M denotes a spectrum, then this is again a spectrum. We can take its infinite loop space. Then the claim is that there is a map from top twiddle M to top M to this homotopy orbit space of the spectrum of H cobordisms. And that's not all, but the theorem also gives us a description of the connectivity of this map. So this is not a homotopy equivalence, but we know something about the connectivity of this map. And under the assumption that our manifold is smoothable that I wrote down at the very beginning, there are explicit bounds that we can write down that I would like to skip. But what we can say is that the connectivity of this map diverges as the dimension of M becomes sufficiently large. So in effect, the bound that we know is some linear function or affine linear function in the dimension of M. And then you know if the larger the dimension of M, the more connective this map is. And this, in fact, uses results due to Igusa. Yes, something like that, yeah. Okay, so this leads us to say, if we want to understand the homotopy groups of this guy, at least in a range, it's maybe good enough to look at the space of H cobordisms. So the next question is, how do we compute the homotopy groups of this space of H cobordisms? And if you think about this, what could this be? So a zero simplex vertex in the space of H cobordisms would be an H cobordism over M. And now what does it mean to have a one simplex connecting two of these? That should correspond to knowing that the two H cobordisms are homeomorphic if we're in the topological category. So the set of path components of this space should be something like isomorphism classes of H cobordisms over M. And we know how to calculate that because the S-cobordism theorem tells us this is the Whitehead group of the fundamental group. And this already suggests that this space of H cobordisms has a connection to algebraic K-theory. On the other hand, if you now try to promote this pi0 statement that we observed to a statement about spaces, then it's not the right thing to consider a generalization of the Whitehead group of your fundamental group, but you should recall, if depending on how familiar you are with the proof of the S-cobordism theorem, that there's actually a step in between. You don't have to pass right from an H-cobordism to the Whitehead group of the fundamental group, but instead there's something called the geometric Whitehead group, which is built out of CW complexes relative M such that the inclusion of M is a deformation retraction. And that's actually the right thing to consider. So let's make a definition which is supposed to turn the definition of the geometric Whitehead group that you might know into, well, we want to make a construction which gives us a space whose pi0 is the geometric Whitehead group. And that goes as follows. Suppose that X is now some topological space. Then we define a category which has a slightly convoluted name for reasons, which I'm going to denote SCH of X. And these are, or this is the category of finite CWs relative X. Let's give these a name, CWs Y relative X, such that the inclusion of X into Y is a homotopy equivalence, which is the same as saying X is a deformation retract. And what are the maps in this category? They are the simple homotopy equivalences. Now, as a sanity check, we can connect back to the proof of the S-cobordism theorem. If you have an S-cobordism, then you do something like choose a handle-body decomposition that induces a finite CW relative to your base manifold, and you consider these up to simple homotopy equivalence, and the proof of the S-cobordism actually tells you that that is enough to distinguish isomorphism classes of H-cobordisms. So there's hope that the nerve of this category may have something to do with the space of H cobordisms. And in fact it does. And well, I've basically just said of what sort of map we would like to write down on pi 0. Of course, there were a lot of choices involved, which doesn't turn this into a map right away. And if you want to write down a map between this implicit set describing the space of H cobordisms and the nerve of this category, you run into all sorts of problems. But the basic idea is what I just said. If you have an H cobordism, an H cobordism, just turn that into such a CW complex, and that's the map that you want to consider. And the theorem that tells us that this is actually a reasonable thing to do has a very long history, and the full proof appeared only a few years ago. It's due to Waldhausen, Jahn, and Ronges. And it tells us precisely what I've been suggesting all the time. It tells us that if we look at the infinite loop space of this spectrum of H cobordisms, this is weakly equivalent to the nerve M of this category. Okay, so now we've translated the computation of the homotopy groups of the space of H cobordisms into the question, how do we compute the homotopy groups of the nerve of this category, of this category, if you want. The involution, that's a very tricky question. I'd like to ignore that for this talk. It's all right. I see why one is interested in that. But it's not that easy, or as easy to describe as one would hope, at least as far as I know. Yeah, right. The problem with that is that if you turn the H cobordism upside down, you don't know what the upper end is. Something else that I've been hinting at is that the space I wrote down here, the nerve of this category, that this should have a relation to algebraic K-theory. I already told you, if we take pi 0 of this space, you get precisely the geometric Whitehead group that you might know. And, well, this sort of suggests that this space should have a relation to algebraic K-theory. Of course, if you want to make this precise, you might want to try and do something like explain what the algebraic K-theory of such a category is. And let me be rather vague about this. So there are various definitions of algebraic K-theory. You usually would like to have your categories to have a zero object, at least. That allows you to do a number of constructions. Like, if you know that pushouts exist, you can take coproducts, but you can also take quotients. And it's very helpful to have a zero object, let's say, and this category does not have a zero object. Even if we say we consider a relative category, where we only look at such CW complexes, which contain X as a deformation retract, and all maps, and think about the simple homotopy equivalences as weak equivalences in this category. This does not really have a terminal object. You know that you can always map back to X, because you can choose an inverse to the deformation retraction, but that's a contractible choice you have to make, which is kind of inconvenient. So instead of saying, well, I only have a terminal object up to some contractible choice, we just slightly modify the definition of this category by saying that each object comes equipped with a choice of retraction, and then things turn out to be fine. Let me fix that in the next definition, which is the definition of the category of retractive spaces. So if we have a topological space again, then we look at the category R of X. This is now the category of finite CWs y relative x together with the map R from y to x, which is a retraction to the structural inclusion that we have. So such that if we look at x maps into y, maps back to x, this is the identity. And then, of course, morphisms in this category are, well, cellular maps relative, cellular maps over and under x. So both relative to x and compatible with the chosen retractions. Note that I'm not requiring more about the structural inclusion than the existence of such a section. That's also kind of the reason why I don't have an H up here. So this category now becomes equipped with different notions of weak equivalence. I might want to consider objects in here to be weakly equivalent if I have a map of this kind, which is just a homotopy equivalence. Or I might also look at maps in here which are simple homotopy equivalences. These are two different notions of weak equivalence that I might consider, and I might also wonder how they are related. So if I think about it that way, then this category are those objects which are contractible with respect to the notion of homotopy equivalence. So weakly equivalent to the zero object in this category, which is x without any cells attached. And now the first point that I was going at is that we have now modified the definition of this category to the category of retractive spaces. Now it actually makes sense to speak about the algebraic K-theory of this gadget. That's due to Waldhausen. That's a definition that we make, A of x. This is the algebraic K-theory. Whoops. Of this category of retractive spaces over x. And now the definition of algebraic K-theory depends also on feeding in the notion of weak equivalence. And the notion of weak equivalence that I feed in, if you want to define A of x, is just homotopy equivalences. And also maybe to connect up to other talks that we had, for example, Holger Reich's, this is equivalent to taking the K-theory of the spherical group ring of the loop group of your space. So that's how this story relates to the things Holger Reich was talking about, because he was talking about K-theory of spherical group rings. And that's an equivalent description of the algebraic K-theory of a space. Yes, that's a good point. This is slightly subtle. So if I say homotopy equivalence, these are only required to be relative x, but not, they don't have to be compatible with the retraction. So now if you look at what we were actually interested in this category of CW complexes containing x as a retract up to simple homotopy equivalence. If we ignore this business with the retractions for a moment, this category looks a lot like a fiber. It looks a bit like take those spaces with our weakly equivalent to the zero object with respect to homotopy equivalence and consider these up to simple homotopy equivalence. This is how you would usually go about defining some relative group if you want to compare two things. And in fact it is. That's another theorem due to Waldhausen, who tells you that if we look at the nerve of that category that we were considering anyway, that we can give a description of this guy in terms of A of x. Namely, Waldhausen describes this as the homotopy fiber of the classical assembly map in A theory. And so now we have finally found a connection to something which is really the algebraic K-theory of something. Well, something you can always say about A theory, but that's also a big theorem, is if you look at A of x, that always contains as a summand the stable homotopy of your space. And then there's other stuff which is much harder to understand. And so, right, if I were to replace A of a point here by the sphere spectrum, then I would know that this assembly map splits, and you will get something that you might know as the diff Whitehead space of the space that you plug in. And now, if you look at this, this tells you, if you're familiar with the language, that the nerve of this category models loops on the PL Whitehead space of X. If you don't know what this means, don't worry. I'm not using it. Yes, yeah, that is true. Okay, so now we've connected our original question about the homotopy groups of automorphism groups to this A theory functor. And well, this is loops on the Whitehead space. So if you're wondering where the name comes from, I guess we've already seen this week. You can describe the Whitehead group as the co-kernel of the assembly map, of the classical assembly map in degree 1. And that leads you to define the co-fiber of the assembly map as the Whitehead space or spectrum. And then the homotopy fiber, if you're working stably, is just loops on that. I think if you want to have something really geometrically meaningful in A theory, you also have to take into account spherical vibrations over your space and somehow twist the involution by that. Yes, I mean the linearization map always exists. Ah, okay, all right. That's one of the reasons. Yeah. That's also one of the reasons why I didn't want to talk about the involutions, because the business is somewhat unclear what the correct thing to take is. If you want to have something which connects up all the involutions in the right way that you may think of. Okay, so something else that Waldhausen has shown about this functor is that it is homotopy invariant, which you'd maybe also would have wanted to use in order to write down this assembly map. And, well, now we're basically in business. If we have a homotopy invariant functor in spaces, we can always write down an assembly map. Let me just quickly recall how you can do that. So let us define a functor A on the orbit category by saying if I have G mod H, in order to make this functorial, in the end I want to map this to the A theory of BH, which is not obviously functorial in the orbit category. So I do something slightly more complicated by saying I take the transport groupoid of G mod H as a G set. Then I can take the nerve of this category, I can realize that. and then I take the A theory of this guy. And this is equivalent to the A theory of BH. Oops. But now has the advantage that we see that it's obviously functorial in the orbit category. Now that we have an OG spectrum, we get an assembly map, an equivariant one. Which now goes from the homology equivariant of some EFG with coefficients in A to A of BG. And if we think again about the aspherical manifold that I started with, then of course this aspherical manifold M is a model for some BG, namely for B pi 1 of that manifold. And of course, if I take F to be the family of virtually cyclic subgroups, then we get the Farrell-Jones conjecture for A theory. Let me also remark about something else. So up here, this may look like computations in A theory don't tell you that immediately how it connects up to computations of the homotopy groups of this homotopy fiber, of this whitehead space. In fact, it does. The reason is that the difference between these two functors is a homology theory, and in fact we can write down an assembly map for all three of these. And since one of the three comes from a homology theory, any isomorphism conjecture you would want to write down is true, and hence this is the remark I actually want to make. The isomorphism conjecture for the homotopy fiber of the assembly map, the classical assembly map, is equivalent to the A-theoretic isomorphism conjecture. So if we now start proving and the isomorphism conjecture and computing things, then this really tells us something about the gadget we're actually interested in. And as you have probably guessed, I wouldn't be writing down this assembly map if I didn't have something to say about it. And I'm also aware of the fact that you have, again, already seen quite a number of lists of groups this week, so I'm trying to keep this short. The theorem goes as follows. The A-theoretic isomorphism conjecture, or Farrell-Jones conjecture, let's say Farrell-Jones conjecture, A-theoretic Farrell-Jones conjecture holds for, let me split this up into 3 subpoints. It holds for virtually poly Z groups. That was done by Mark Ullmann. Myself. It holds for hyperbolic groups. Or, since we've seen the notion yesterday, more generally, it holds for finitely V-sig amenable groups. And also for cat0 groups. So something that you didn't see yesterday is there is a variant of the notion of finite V-sig amenability where you don't require an honest action on some space, but you only look at homotopy coherent actions, and that's used to prove the conjecture for cat0 groups. And we can also prove the conjecture for this notion. And this is due to Niels Edwin Enkelmann, to Wolfgang Malte Pieper, Mark Ullmann, and myself. And then in addition, let me also mention this, we also know that the conjecture holds for virtually solvable groups. This is due to, let me get the alphabet right. Daniel Kasprowski, Mark Ullmann, Christian Wegner, and myself. And if you're somewhat familiar with proofs of the Farrell-Jones conjecture, then these are sort of the base cases that you require in order to build off of that, using just general properties of the assembly map. So there's number of inheritance properties that you can use, which also hold in A theory. And since we don't provide a specific proof for hyperbolic groups, but for this notion, you can extend this class of groups to all other sorts of things, and that's all, of course, then due to a lot of other people. You've seen the long list in Holger's talk. So if you want to sum up, what I've been trying to say is that basically at this point we can say we know the A-theoretic Farrell-Jones conjecture in the same generality as they know the K and L theoretic Farrell-Jones conjecture. Yes. Well, not modules, but controlled retractive spaces. Oh, models, yes. So the plan is to say at least a few words about this at the end of the talk. But let me first remark about two other things. This is all nice, but I've also said that A theory is a kind of complicated functor to understand, so you may wonder, does this actually facilitate any sort of computation? And it does, to some extent. For example, recall I was speaking about this closed aspherical smoothable manifold of sufficiently high dimension. If we assume in addition that pi1 of this manifold is hyperbolic, then we can write down some quite explicit formulas. So let's now assume that the dimension of this manifold is at least 9. Then, with a little additional work, you can compute the following. If you look at the homotopy groups of top M, which was the space of self-homeomorphisms, then these are isomorphic to a big direct sum, which is indexed by conjugacy classes of maximal infinite cyclic subgroups of pi1 of M. Well, I'm going to put restrictions on K. This is, so we have a direct sum, and then we have here pi k plus 2 of, okay, since I haven't introduced the notation, I should probably write pi k plus 1 of that guy up there. M, sorry. And for those who are familiar with the notation, I have the feeling this should be on the blackboard at some point. Pi k. This is pi k plus 2 of whitehead top. Oh no, sorry. This is S1. Sorry, that was. And this holds for k between 1 and, now, oh, here I have the explicit bounds that we know. the minimum of n minus 7 over 2 and n minus 4 over 3. And 9 minus 7 divided by 2 is 1. Oh, 5. Oh, yeah, 10 is probably better. Yeah. Yeah, I guess 10 is better. Yeah, it was kind of empty for 9. But something else that we can also... Well, that's what I'm going to write down next. And the statement for pi naught is the following. For pi naught, we don't have a direct isomorphism. We only get an exact sequence. And this exact sequence looks as follows. So we look at pi 0 of top m. And then this projects onto the outer automorphisms of pi 1 of m. Recall that I claimed that this is pi 0 of top twiddle. And the kernel looks like that guy up there. So we have again this big direct sum indexed by maximal infinite conjugacy classes or maximal infinite cyclic subgroups. And then we have here, let me now just write pi 2 of whitehead top of S1. Well, if I'm saying I have a hyperbolic group, then the center is trivial. Well, so S1 is the classifying space of Z. That's BZ. Since we have an aspherical manifold, we know that pi 1 is torsion-free. So the Farrell-Jones conjecture tells you things are induced up from infinite cyclic subgroups. And now, since we have a hyperbolic group, you know that the orbit category has an extremely simple structure, because every infinite cyclic subgroup is contained in a maximal infinite cyclic subgroups, and those have trivial normalizers. And that's how you end up with this direct sum. So this S1 is, if you want, BC. So that comes more or less out of this Hochul-Lim formula that you can write down for the domain of the assembly map. And let me add one other thing. No. It's this Whitehead thing is precisely the non-homology part of A theory. So this Whitehead thing is the co-fiber of the assembly map. And right, so one other thing. At least if we're looking at pi 0, and then we have pi 2 of Whitehead top of S1 here, that's been computed. Lars Hesselholt has shown that this is, so he has a more explicit, or slightly more explicit description. Let me just say abstractly, this is isomorphic to a countably infinite sum of Z mod 2s. Yes, this I can add. This makes things clearer. Mainly the involution, that's the claim that if you look at the Bars-Hellas-1 decomposition for A theory, then you get two nil terms. The involution exchanges these two nil terms. So if you mod out by Z mod 2, which we have to do at some point because we only can identify something with a homotopy orbit space of the H-group ordisms, then we just identify these two copies and are left with one copy. And that's the thing appearing here. One other thing that I'd like to say, but maybe let me not write this down, but just say in words. If you are familiar with the history of the Farrell-Jones conjecture, you will know that Farrell and Jones originally wrote down this conjecture not for the A-theory functor, but for the pseudo-isotopy functor. And pseudo-isotopies haven't appeared yet. And I'm not expecting you to know what a pseudo-isotopy is, but let me just say that, or maybe let me write this down as a quick remark so I can mention two names that have already been on the blackboard, but nevertheless. Let me just say that the A-theoretic Farrell-Jones conjecture is equivalent to the original one for pseudo-isotopy. And for me to really claim that this is true, I should reference the PhD thesis of Niels Edwin and Malte again. Oh, now I'm referencing there. Oh. So Malte and Niels, they have worked in their PhD thesis on the question to show that this is really the case, because I mean it's not enough to know that pseudo-isotopy, that homotopy groups of pseudo-isotopy are abstractly isomorphic to something, but you really have to construct functors, natural transformations on the non-connective spectra related to these guys, and there are some things to show. The first one actually is to understand in which sense pseudo-isotopy is a functor. And if you want to know more about this, better talk to Malte. All right, so with 10 minutes left, I would like to say a few words about how you approach the proof of the theorem I wrote down up there. Now, the ideas that go into the proof are basically, or they are the same ideas that are used in the proof of the Farrell-Jones conjecture for K and L theory. And roughly speaking, you could say the idea is to think about, so what you want to do is you want to build K theory out of certain cycles. And these cycles are supposed to come equipped with the notion of size measured in a space that you fix beforehand. And then in order to describe the domain of the assembly map, which is the homology theory, what you want to do is you want to say, I look at all K theory classes which can be represented by cycles of arbitrarily small size over my space. And then the claim is if you make sense of this correctly, then you can actually describe the domain of the assembly map as the K theory of something. And the domain of the assembly map, and the assembly map is simply given by forgetting the control of your cycles. So the thing that you want to do is to write down something analogous for A theory. And let's recall quickly how I defined A theory. I said A theory is the algebraic K theory of this category of retractive spaces. So these were relative CWs together with a retraction onto X. There's an equivalent description of this, which goes as follows. This is, so to speak, the equivariant picture of A theory. Let's say now that X is not only a space, but a G space, and let's say G is only a discrete group for now, then we can look at the category Rxg of equivariant retractive spaces over X. So what is supposed to be? Basically what you will probably write down yourself. So this is the category of GCWs Y relative X. Oh, let me also already add free here. Free GCWs relative Y, which are co-compact relative X. So we only attach finitely many equivariant cells to X. Together with an equivariant retraction from Y to X. And morphisms, of course, are again cellular equivariant maps over and under X. So just the same thing as in the non-equivariant case. And something that you observe is there is always a functor from this equivariant guy to the quotient of X by taking quotients. And if you know that X is in fact a principal G bundle, then this is an equivalence, because then if you have an object down here, you can just pull back along the projection and you will get such a free GCW, and that sets up an equivalence of categories. And now, for those of you who know what the linear models for controlled ktheory look like, you can already use this to set up an analogy that you may want to use if you're wondering what a controlled retractive space should be. Because if we look at these guys, we can define a functor to finitely generated free ZG module chain complexes by mapping such a retractive space to its reduced cellular chain complex. And now if you know what a controlled module is supposed to be, then you already get an idea of what a controlled retractive space should be. So what we want to do now is we want to look at such retractive spaces, but now we don't want to take arbitrary ones, but we want to say something like we equip our retractive spaces with a reference map to, well, in full generality, some core space, but you may think of a metric space. Then we want to say that the attaching maps of our cells only satisfy a certain control condition, or that they are only glued to cells which sit in a bounded set around the set over which our cell is based. And let me make this precise. So maybe a quick question, do people feel comfortable with the notion of core space? Yes? Okay. If Arthur hadn't said yes, I would have only written down something for metric spaces, but now I'm doing core spaces. The difference isn't that big. So let's say that Z, and let me call my set of entourages U, is a coarse space. Now we'd like to say what it means that some retractive space is, or I should say G coarse space, is controlled over this G coarse space. And as I said, we want to make a statement about attaching maps. So I want to think about cells of Y being labeled by points in this coarse space. And there's a very simple and combinatorial way to do that. So let's say that YR is a retractive space over X. And I can look at its set of cells. If you recall your teaching in basic algebraic topology, you know that this is a well-defined notion because what a cell of a CW complex is depends only on the skeletal filtration, not on the choice of characteristic maps or anything. This is in fact a G set, since we had a GCW complex. And now we want to label each of these by a point in Z. So we choose a map kappa from the set of cells to Z, which should be G equivariant. And then we would like to express what it means that cells are only attached to other cells which are boundedly far away or in a controlled fashion away from the point which we have assigned to that cell. So we say that this gadget now, Y equipped with the additional map kappa, is controlled over this coarse space. Or maybe I should only say U controlled. If the following holds, and there are various variants of the definition that I'm going to write down. Let me just give you one. Let's say if for every n in n, we look at the following. Consider cells of dimension at most n in Y. And now we look at the cells to which this cell is glued, and maybe not directly glued, but in several steps, meaning I look at all cells contained in the subcomplex spanned by C. So let's look at cell C prime in the subcomplex spanned by C. Then I can compare the points in my core space which I have assigned to these cells. So I can look at the pair kappa of C prime, kappa of C. And now I want this set to be controlled in the sense of my core space. So I'm requiring that there exists in U such that this set is contained in U. And this is a notion of control which now tells you that the attaching maps of cells don't spread my cell out too far over my core space. And that's the basic notion that you start with when you define now controlled objects, and you can define controlled objects over the cone that Uli also talked about, and then you get models for the domain of the assembly map, and the entire machine gets running. That's it. Mm-hmm. Yes. Mm-hmm. Yes. Yes, so something you can say in general is that if you look at this linearization map from A theory to K theory, So when I say A theory here, I actually mean non-connective A theory. That's a subtle point. But then you know that this linearization map is always two connected. So as a matter of fact, in low degrees, we haven't proven anything we didn't know before. The interesting stuff is really in the higher homotopy groups. And if I speak specifically about A of BG, so if I plug in an aspherical space, then it's also known that this linearization map is a rational equivalence. I don't know whether there's more to say if you look closely enough at the fiber of the linearization map. I guess that goes into some computations about atheoretic null groups. Yes. So I think there's a paper by Grunewald, Klein, Matschko about nil terms in A theory, and I think they look at the fiber of the linearization map to do computations.